Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Of Southern California. As many of you know, Cyrus has a long background in database, but he's also been working in geoinformatics for many years. And he's going to tell us about both his research and the research of the larger GeoDec project at USC, which includes researchers in artificial intelligence, data mining, computer vision, and computer graphics as well. So Cyrus?
Okay. Thank you very much, Rick, and thank you for having me here today and also showing up at, I think 10:30 is the time that usually we do work, so I appreciate you. Maybe your boss are not appreciate it as much as I am, but for skipping work and listening to the talk. So as Rick said, this is not mainly just my own work. It's a collaboration between 5 different faculty members at USC working in different areas. So it's a truly multidisciplinary project that we put together. And one reason that we can do things like this is because of this center at USC, which is called IMSC, or Integrated Media Systems Center. The center started in '96 and got funding from NSF as an engineering research center. There are about 20 to 25 ERCs, or engineering research centers, in the nation in different areas. And the way NSF works is that if one center, for example, they establish one center for multimedia, then they're not going to have another center in that area. So IMSC is, for now, the National Science Foundation Center in the area of multimedia. And one of the things that basically the center encourages is this multidisciplinary projects that you put a bunch of faculty together. And this is a little bit different from the typical way that universities work, because usually faculty do their own research and submit proposals and get funding, and their work don't get that much integrated with each other's. But because of the center, we had the opportunity to define this new project, GeoDec, which stands for geospatial decision making. And then the technology developed within GeoDecs are technologies that are useful to enable the geospatial decision making. And I'll tell you a little bit what that means. So what's the mission of GeoDec? And this is just a one-sentence mission. There are some keywords there. Some of them, for example, rapidly is important. We want to be able to build virtual environments, but we want to be able to do it rapidly. So this basically, for example, distinguishes this work from everything done in Hollywood, because they do build very realistic, sometimes 3D environments for animation, but they spend a lot of time, a lot of human resources, and that's something that you don't want to do all the time. Accurately is another important keyword here that and I'm going to show you examples, that if you don't do things accurately, then this last piece would fail, the part that you want to do query and analysis. If you don't have an accurate fusion and modeling of the environment, you cannot do a good job in querying and then data analysis. And then, of course, realistic and then information rich is another piece, which means that we just don't want to build a 3D environment that you can just navigate through it. We also want all the back-end information associated with that environment and being able to also access that. So look at it more as a GUI, as a very fancy GUI to access data underneath. So these are basically the main challenges we defined and we proposed to our management, which is raise. And there was a hidden message here, but I don't think they actually got it. So we want the as I said, realistic rendering, accurate fusion of information. I'll talk about this one because that's the area I worked on most. And then query and access. We don't have that much of it yet, but I show you some examples of things that we do have right now. And then the scalable infrastructure. This is important because as I show you in the system, you have several streams of video, the 3D models, all sorts of data, and you need to somehow make sure that your underlying infrastructure scales. Otherwise, you cannot basically scale the system up. And then, as I said, efficient time to build. So one of the questions actually everybody asked me, and Rick asked me this morning, was that, okay, so this is cool, like, for example, Microsoft Virtual Earth or Google Earth, people go and play with it, but what is the real application for these sort of things? And interestingly, when we started, we were not really thinking of the Google Earth or Microsoft Virtual Earth type of applications. We were at universities, we need to get funding for research, and the main sources of funding are these like DARPA and ARDA and these sort of government agencies. So we needed to basically make a case to them that what's the usefulness, and that was not very difficult. So you can immediately see that such an environment that you can have access to all sorts of data would be very beneficial for all sorts of things that is of interest to DARPA or ARDA, for intelligence officers, for example, to ask queries about an area, for rescue response and so on, as well as for just the regular urban planning operations, for example, which is not really that much of a defense-oriented, but even from a city planning aspect. And then another important area that we're looking, USC these days trying to be a main player in the games, in computer games, and they have all sorts of things happening in that area. So one of the ways that we market things within USC was that being able to build a 3D model, realistic model with all sorts of information would be a very nice platform to have games on top of it. So definitely it's useful there as well. And then the purpose for building this, or actually coming up with this vision of GeoDec, is mainly first to be able to work together as a team, as I told you about the different people involved, so that we can write proposals. Because one of the issues is that when you write proposals to federal agencies, like NSF these days, they usually want multiple PIs on the proposal, so they don't want a single PI proposal anymore. And then the way that usually it works is that 4 or 5 people come together just 1 month or 3 weeks before the proposal deadline, and they start talking and okay, what you do, what I do, and then try to put things together. And when I served in many of these panels that review proposals, and it's very obvious. I mean, when you read the proposal, it's immediately obvious that these guys just got together last minute and put together a proposal, right? And it's not really a multidisciplinary work. It's just that they patch it like that. So one lessons we learn is that you should actually do some work first together, so that you really know what are the what NSF calls turbulences between these different areas. What are the challenges from one area to the other and back and forth? And then you can write a nice proposal. And then the proposal doesn't show as like just some pieces. So that's very important for us. And of course, having a demonstration that you can show to people around, that would attract funding from corporate. So we already have some funding from Chevron and Google, and hopefully soon from Microsoft. We have funding from Microsoft, but for a different project. So this is just a very abstract block diagram of the system we want to design, or we want to build. It's basically mainly dealing with all these different sources coming from like it being satellite images or point data, gazetteer data here, raster maps, video streams, and so on, and being able to fuse them and be able to query them. So right now, I say in the demos that I'm going to show you, we are mainly in the blue area. So we are mainly just showing the virtual environment that you can navigate through it. And just a little bit of a querying, but not much. What we hope to get is here, where you do more than just visualizing and doing simple queries. You actually start doing data mining and data analysis on top of the databases that you collect. So that's basically where we want to go. So that was the general idea about what this system is about. Now, today I'm going to talk about 3 of the components very briefly. I guess briefly on these 2 because those are not my areas, so I'm not going to go into detail because I cannot. But the last one I do a little bit of more detail. and then tell you basically what's the status now, and hopefully I show you a couple of quick demos, some video clips that we put together from the demo, and then where we are going. So I don't know, maybe just a quick, if you have any questions right now about the general project, we can take it now. It's okay to be more interactive rather than just wait till the last minute.
Are you already participating with electronic arts?
Are we, sorry?
Already participating with electronic arts?
Oh, the electronic art piece was, so those are the, not the ones that are already funding us. These are the sources we're going after. The electronic arts already supporting USC's game work. So the plan is basically we are now working with the, I don't know if Mike Zaida is the person who's running the game pipe at USC, and we're working very closely with him. So the idea is that we do get some research going on with Mike, and probably sending a proposal to DARPA soon. And then as part of that, we might get some EA funding afterwards. But right now, no, nothing on this specific project. Yes?
Yeah, I guess I would have expected to see some more from users of those systems. Mm-hmm. So, you know, I don't know what, if I'm running a bus company and I've got buses on a map and mm-hmm. I want to draw them around, mm-hmm. then, you know, that's an application that's built on top of this stuff. Or mm-hmm. another one might be marketing stuff, where years ago it would have been done with map info. I don't know how it would be done today. But, you know, if I want to say, look at my territory mm-hmm. and see where are the high dwelling opportunities, where my market share is, and all that, mm-hmm. They would have overlaid on top of a map mm-hmm. tiger census data. And so the question is, how can I visualize tiger census data, sales figures, and something that might make sense to a sales and marketing?
So we do have one, I guess, or two real users, but we're just starting to work with them. So I can give you some examples. I don't have them in my slides, but afterwards I can tell you about some of the examples. About one user group is basically urban planning folks, and I will tell you the sort of things that they are interested in, how something like that can help them. And then another basically user group that we are kind of, they're not real users yet, but the ones that we are using for sending proposals are basically intelligence community, and the type of queries and the type of questions they are interested in, how this can help. So I can tell you about some of that, but I don't really have war stories yet about real users because this is, as I said, just started. This project started actually June this year. So we're just building the base and trying to attract funding for them. But afterwards, remind me, I tell you a little bit about some of the users. And I use some of the example queries actually during the talk to motivate, so that might be also answering some of your questions. Okay. All right, so the first piece was basically the computer vision piece, which is done by Professor Ram Navteq's group, and basically working on constructing 3D models of buildings. So the objective is how to build these 3D models both accurately and also quickly, because as I said, the rapid development is an issue. And then there are lots of challenges about the complexity of these structures and so on. And then also you don't want to basically have a fully automatic system that wouldn't work is not good, because I mean, you eventually want the accuracy, but at the same time, a system that requires a huge amount of interaction from the users, and basically the users get very tired working with the system, is not good either, because that basically is the other dimension that I told you, is rapid development of these things. So as you see, these are the two different metrics that if you want to satisfy both, you need to find something in the middle. And this is basically what these guys did. They come up with this system they call IMBS. This system was built actually for the past 4 or 5 years funding from NGA. NGA stands for National Geospatial Intelligence Agency. It was NEMA before. And they support research, and they support it at different phases. And the last phase is something that's basically ready to become a product. And these guys did get funding all the way to the last phase. So this is a pretty much ready-to-go system that it can be used. And the way it works is basically you get two images from two 2D images from an area, like an area photograph. And they don't necessarily need to be stereo images. So just 2D images from different angles, as long as you know the parameters. And then the way it works is that it does require human interaction, but the human interacts with one image at a time. It's not like that they need to wear a stereo goggle or anything. So they work with one image, and then that's actually very good for fatigue. And then with one image, they basically click on some points around the corner points, for example, of a building, and then the system automatically calculates the height using the information from two images and generate these boxes, for example, around the buildings. And then you can see, for example, what's missing or what's extra or what does not match from one image to the other image, and you fix it. So it does require some clicking and interaction from the user, but the feedback these guys get from real users working with the system was that this is very easy to work with. And that's why NGA actually supported them all the way to the last phase, because they thought this is a useful product. So I can show you some of the results of the models built from these images. We have actually, I have a comparison result with Google models. So this is an area in DC modeled by Google. Especially look at these buildings here, this one, for example, or these boxes here. And these are now the models built by our system. And you see that you do have the holes and the details of the model. And this whole DC area, they built it in half a day, the model. So it is pretty quick. But I should say that this was done by the person who actually very familiar with the system. So it might not be as fast for a random person working with the system. But if you know all the commands and stuff, then it's actually pretty quick. So the first step for GeoDec is building these models. And that's we use IMBS to build these models. Now, after building the models, as you see, these are just white blocks, right? They're not that appealing visually. So the next step is to put textures on these models. And we talk about both static and dynamic textures, and I tell you what dynamic means, because I guess static is obvious. So the issue is that if you just have aerial views, you can get this sort of information about an area, or you can get streets and roofs and so on. However, you do need ground views to actually capture the facades of buildings and so on. But even if you have those pictures, usually it's the case that you have occlusions from, for example, from trees and other things in front of the building in the image that you have. So that's one issue to how to reconstruct the area behind the tree, for example, when you do the texturing. And then you have this other issue that you might have different images, and you want to be able to fuse them in order to get the texture of one building. And finally, there might be cases where you don't have any information about an area, and you want to be able to synthesize based on the other textures around that area what would be the texture of the missing area. So these are the issues that our computer graphic folks, Ulrich Neumann, is working on. And they actually have a bunch of algorithms for the fusion, for the removal of these occlusions, and also for synthesis. Again, I'm not going too much to the details of how these things work, because I don't know much about them. I just know what they do. I don't know how they work. But the idea is that the result is pretty good. So if you look at things like different images, this is a building at USC campus, and we use this for our second demonstration I'm going to show you. And you do get uncalibrated images, and then the result is a nice texture of this building that then you can use it for texture mapping. Now, we basically not only do the static textures from pictures, photographs, but also we have real-time or maybe non-real-time even video streams of an area. So if you do have basically bunch of, like in this case, 5 different video cameras taking video from an area. And this is an area in Washington, D.C. And this actually has an interesting story because my colleague Ulrich Neumann, he actually went himself to D.C. We wanted to do a demo for NSF, and we wanted to use D.C. as the location. He went to D.C. He basically asked for a very specific room that has the view, and then he put 5 cameras on the window and just sat there the entire day, and he ordered room service. People come in and went out, and they saw him taking 5 cameras of videos from this area, from the hotel room. Nobody asked a single question. So, and you should look at, actually, Ulrich is a tall guy with blonde hairs and so on. So I told him it's very good that you didn't take me with you, because that would definitely be a problem. But let me show you the quick video maybe now. So as a result of mapping these video textures on top of the on top of this DC area. Okay. So this is basically the result of putting those 5 cameras on the models that Ram Navatia built. Let me just play it quickly again. So you see, for example, that there are no cameras here, so the cars disappear. And then you see these poles that are kind of bent, and the reason is this is just a flat video put on the but still, from some angles, you see that it's pretty, I mean, the trees actually look 3-dimensional, even though they are not separate objects. They're just within the video itself. But look kind of realistic and cool. So that's basically the second step. And you can get the same static textures from the video as well. So if you have a bunch of video cameras, you get both the static and the dynamic textures, and you get a realistic view of the area. So now basically that helps for the visualization, because now you have the buildings, you have 3D models, and you can navigate through them. But there is no information behind them. You don't know what that building is, where it's located, what's the street, and so on. So that's basically the last part. Here's just one example for the emergency response application, if you think of those as users, is that it's also for intelligence application. You might want to, if there's a disaster in an area and you have a 3D model, it's not just sufficient to look and go navigate around, but we might want to ask questions, for example, what's the building, what's the impact of this disaster on the transportation network around the building, and so on. So you want to get some more information about that area, not just. And we do have actually technology. I'm not talking about this one too much, but we do have. I show you how you can get transportation maps and stuff like that and put it on the image and on the model actually to ask queries. And then we even look at public websites like property tax website, and they have lot sizes and things like that you can use that information and label the buildings very accurately based on the information you get from that. So as you all know, there are abundance of geospatial information available both now publicly and on private databases. You can get very high quality imagery. There are all sorts of maps around on the web. Vector data, basically things like road network and transportation network, power utility, and so on. Lots of elevation data, digital elevation data available that give you the height at different locations at different resolution. A lot of gazetteer point data, like we had a project with NGA, and they gave us actually a database of almost the entire world that tell you, for example, the lat and long of a point, and then what that point is, whether it's a factory, and all the information you have about that point. So a lot of point information, both directly in databases and points that you can get out of other sources. as I told you, in addition to just pure geospatial data sources, there are lots of non-geospatial sources, like just regular websites, that they have geospatially related data in them. An example is the property tax site. As I told you, it has the information about different addresses, and you can basically wrap these and query them as if they are a database. Lots of temporal information, like, for example, this is a website that has the train schedule of all the trains within Iran, and this is a public website and has exactly the start point and end point, and then the schedule. I show you how we can use this later. Other sources of temporal data you're aware of course, there are lots of traffic flow data, GPS data, lots of video cameras these days all over the place that you can basically get video streams, weather information, and so on. So a lot of temporal data as well. So the problem is that, yes, we do have all these sources, but how we can actually integrate them, fuse them, so we can start asking questions. And you might say, okay, all the GIS systems like Esri products might do this, but that's not really true, because Esri is just a fancy user interface on top of this data that it just give you different layers on these different sources that I told you, but they already need to be accurately matched and then already correlated, basically, so for Esri to be able to show these layers correctly. And I'll tell you a little bit more about that. And what now we are working on is just general framework that you can build. My colleague Craig Knobloch already worked in this general area of information mediators, of information integration, which is not geospatial, but just regular websites and things like that, that how you build a general framework for a mediator that you can ask a query and you don't care where the data comes from which website, from which source. It just goes and reason about your query, come up with a plan, and the plan gets executed on these different sources and you get the result back. We want something similar for geospatial, and the challenge here is that your mediator now needs to be able to do geospatial reasoning. And that's the part that, for example, you need to know that if you say one city and then you say another, like river, you somehow need to know that the river is inside that city. And that's the knowledge that you can only get if you do geospatial reasoning based on geocoordinates and figure out, okay, there's an intersection between that river and that city, for example. So that information mediator needs to be enhanced to support this sort of reasoning. But then the result would be a very nice geospatial mediator that you can send random queries, and then it, again, does the planning and go and get the information. So that's where mainly my research and Craig's research focus on in this project. I give you 3 examples of the integrations that we faced and we tried to fix. One was the integration of road network data and imagery. The other one, the integration of maps and imagery. And the last one is integration of temporal data and imagery. And I show you example challenges of each one of them and how we approach them. So the first one is the vector image fusion. And the challenge is that because of all these problems, that you have different geographical projections, data collected at different scales, and so on, you might have a satellite imagery like this, and you might have a vector data, which is road network data on red, but you see that actually they don't match. So the road network data is not exactly on the satellite imagery. And so I'll tell you later what this caused, but the solution to this right now is that you need to find a bunch of manual control point pairs between these 2 different sources and then do the transformation so one of them matches the other. Now the problem is that, and that process is called conflation, but the problem is that finding these control point pairs is something that you need human in the loop. So the human needs to go and find these control point pairs. And we look at see how we can do this fully automatically without the human in the loop. So before that, let me show you some examples of right now, this is an area, I guess, in Missouri. Google, you see that this is the vector data, the red one. I don't know if you can actually see that. And then the white one is the actual satellite image. It's not that bad. I mean, still they don't match, but it's pretty good. And I think the vector data is they either somehow manually fixed it or they have a better vector data. The vector data that usually people work with is what Microsoft has, which is this one is, I think, Navteq. data. And we have Navteq data as well. And that one is a little bit worse than this one. And Navteq is actually very good quality vector data already. I mean, if you work with Tiger, for example, that's even worse than Navteq. So even very good quality vector data, still it may not match because of all the problems I told you. Now, what we did is that we started with the Navteq data as well. So this is the red one, and if you remember, this is exactly the same location as the Microsoft example. And then we did the conflation automatically, and now we have the blue line as a result of our automatic conflation. So this is done without any human in the loop for the conflation piece, for finding the control point pairs. Now, one question you might ask is that, OK, so what's the big deal? Visually, I can live with this red one being here. I know that this is really the road, and the road is there when I look at it. But the thing is that once you move this thing here and you have the blue line, what you're really doing is that you're inheriting all the attributes that came with that vector data now on the right location on the image. And this includes the lat and long, for example, information, includes the number of lanes that you have on that road, how wide is that road, and all sorts of information. So here is a motivating example why that's important. So if you have, for example, two of these and you put them and they don't match, but then you do the conflation and they do match, now that you know this is exactly the road and the coordinates, and you know how wide it is, and you have the scale information and so on, then you might be able to do a much better job in coding the addresses. Because then you have all the information. This image is not a bitmap anymore. Now it has all this information about how wide is this place. And again, as I said, you can even get more information from things like property tax website to get even lot sizes and so on and do a better job. And then once you get the geo coordinates and the address, you can go to white pages, yellow pages available on the web and get all sorts of information about, for example, a house or a road and so on. So that's just an example of why you want a very accurate fusion of these two data sets. Yes?
Now, on this example and on the previous one, you've improved the conflation, the alignment by a lot, but it's still not perfect.
No.
On the previous one, there was a certain growth
Absolutely.
that went, yeah, the blue line on the S part doesn't match.
Right.
So is this sort of the level at which you think you're going to stop, or are you going to try to get it all the way down to the center line of the road?
Very, very good question. So we are. So this is the result of our kind of. I think after this we did some improvement. I don't know if those improvements would fix this or not. And I'll tell you a little bit about different techniques as I go through some of the details that we try to improve. So we do our best to improve these as much as we can. But you're absolutely right. The end results, you still might have. You still might end up with problems. So one thing that we try to promise within our system is that we keep it the same or we do better. So the plan is not to do worse, because you might. I mean, you might start doing transformations and you mess up something which was already correct, right? So we do the same or better. And then for areas that you cannot eventually match, we are working on a piece that I don't have slides on it, but at the end, basically, you can think of it in the kind of, I hate to use the Google Earth example, but think of it in the Google Earth scenario where you have all the people who are interested in contributing stuff to Google Earth, right? So the idea is that we build a piece of software, right, that you can fire it up from your browser, okay? Look at the area. This is your house. You know exactly how things are, right? And then you go and click on a couple of things and fix those vectors that are bad, and then put it back into the system, right? So next time somebody come and look at that area, you fixed it for them, right? So
assuming you can trust.
You can trust. So all those issues. But I mean, the example we use, for example, for the facade, because we trying to have the same. Philosophy actually for all the pieces. So the other piece was these textures, and then we said, you know, we don't have textures for everywhere, so we might just put wrong textures. I mean, what the best we can do. We know the building here and the building there. We just put a wrong texture in the middle, and then that happened to be a Starbucks, and then Starbucks come and say, oh, all my textures are wrong, and just put some effort and fix all the Starbucks textures, the entire US, right? And then Burger King says, hey, all the Starbucks textures are correct in Google Map. I should go and fix my texture. So that's the kind of idea. So at the end, you do need users. I mean, you do need humans to actually fix things. So you can do as good as you can, and then afterwards, yes, you still need to do some manipulation. But these fixes are not that tough. I mean, once you get there, then a couple of points clicking here and there can fix these problems. But you're right, we can't fix it 100%. So so that was an example. Now let me tell you what's the approach that we have. So the approach, I'm going to go through these boxes more in detail, but just give you the big picture. The big picture is that you get these two things as input, and you have the lat and long of their corner points. And the first thing you do, which is the piece that's usually done by hand, by humans, this is the part that we do automatically. We detect some control point pairs. And I tell you later how we do that, but basically we use the intersection points as the control points. Okay? So once we do that, then right there we might do things wrong. I mean, we might find something as an intersection on the image which is not really correct. So we go through a filtering phase to get rid of all those wrong ones. And then once we have those good control point pairs, then we do the conflation approach, which would actually fix it. Which basically transform one data set to match the other. And this transformation is not a global transformation. That's why we need those control point pairs. So you do a bunch of local transformation on the triangles generated by three control points. So let me go through each one of these and tell you the technique we use. The technique we use for the control point detection is basically so. Let me tell you the history here. The history is that control point pairs, especially for roads, the road intersection is a very good feature. And even when human users do this, they actually use the intersection. So they click on the intersection on the image, they click on the intersection on the vector, and then the system uses those as the pairs. The approach used by computer vision folks was that we'd get an image, and then we basically find all the intersections within that image. And then these are our basically candidate control points. The approach we took is a little bit of a mix. And the mix is that if you just get an image, and I guess Rick can tell you more, and try to find all the intersection points on the image without any extra knowledge, it's a very tough problem. You have all sorts of problems. You have shades on the street and so on. And it's not easy to do that. However, you do have a lot of information already from your vector data. So from vector data, you already know that there is an intersection around this area. It's not accurate, but it's at least within some range. You can basically get that information by just knowing the quality of the vector data that you're getting. You know that there's an intersection around this area. But more than that, you also know that there are, for example, in this case, there are 3 streets that intersecting. So, and then you also, as I said, you also know how wide these streets are from the metadata in the vector data. So you can kind of build a template and say, oh, I'm looking for something like this. Okay, so you not only know that what you're looking for, but you also know a very limited area that you want to search for it. And that actually makes the system both faster and more accurate. But we still need to do some classification to figure out for each pixel whether it's an on-road and off-road. And you can do this by training using Bayesian classifiers or other classification techniques. Actually, this is one of the things that we improve. So the result I show you would use Bayesian classifier. I guess now we are using support vector machines, and we use all the 3 colors. And we're doing better. And we fix some of the problems because we did find some wrong intersection points before. But anyway, so as a result of that, basically you get this image as white pixels and black pixels. So the white ones are on the road, the black ones are off-road. But what's important is that you don't need to be 100% accurate. It's okay to miss some points and classify them as off-road. Like this tree, for example, here, you classify it as off-road even though it was on-road. Or the other way around, have some points that are off-road and you classify them as on-road. This is okay because you're looking for a very specific template, right? So you can tolerate a good amount of error. And then after doing your search, you say, OK, this is the best match that I found, right? And that this would be your intersection point. So you already see that the system is pretty much robust to noise right here because you're looking for something very specific within a limited area. But even more than that, after doing this, so the idea was that, okay, I find all these points on the vector, and that's easy, right? Finding intersection points on vector is just a simple computational geometry problem. You find those, then you basically use the technique that I told you, and around those find the intersection points on the image, right? But you still might have done some wrong classification. For example, I think, which one is wrong? I think this one, I can cheat. Okay, those are the wrong ones. So you have some wrong intersection points here, right? That you identify them because you thought there was an intersection there because of all the road classification errors and so on, but that's not correct. But now the good news is that, or this one is obvious, right? This is a wrong intersection point. It should have been here, but because you look in the area around here, the template happened to match here as well, right, because of all the classification. But the good news is that you don't need to find all the intersection points. You only need to find a handful of intersection points that are accurate. Okay? So at this step, basically, there are many techniques like the vector median filter that you can use. And basically, what it does is basically generate a vector from the one of the sources to the other, and the size of the arrow is the size of the displacement, and the angle is the angle of the displacement. And then you basically do some technique which is robust to noise, for example, finding the median. Median is more robust to noise than medium. So for example, you do that and find out what's the median vector, and then basically say, I will keep k% of the vectors around this and just drop everything else. Okay, and that's fine. I mean, you might drop some good stuff as well, but that's okay. As a result, basically, you get a number of these, but these are all good. These are all good intersection points. And then that was the filtering, and then you do basically the triangulation of these points and do the transformation. So intuitively, the way it works is that you can think of one of the, and that's why it's called rubber sheeting. You might think of one of these sources that is on rubber, and you move the rubber until it matches the other one. And the reason that we say rubber is because it's a bunch of local transformation. It's not a sheet that you just do a global transformation, right? And that's the purpose for these triangles, and that's how it works. So after that, basically, you do the conflation. We did a lot of experiments with metrics on our technique, and these are in papers in case you're interested. So we actually identified very harsh metrics actually for figuring out if, for example, a road is inside the buffer of the image, how far you are from the buffer, how much you're out of the buffer, and so on. And we did pretty good in all those numbers. I don't want to report on those numbers, but if you're interested, you can see those in the papers we have. However, I just want to show you some of the results visually. So here is the red line is the tiger line. You remember I said that tiger is pretty bad. So as I said, Navteq is the best in the accuracy of the vector. So tiger is pretty bad, and so we do fix those. And the yellow one, as Rick mentioned, we do still have problems. But some of these are really we can't fix at all, because this is the reason is that there's a curve here, and all we got was a line. So we cannot, at least currently, we cannot take this line and make it into a curve until we use a technique like snake or something. Yes? Where are the errors in these databases come from? I show you at the beginning. So they are, for example, these are coming from different sources. So this vector data, for example, it takes a different projection from a different image at a different time. And then this image is a new image you got from a different projection. So these are basically, or they're at different angles and so on. Taken.
So part of the error is the fact that you really don't know where the image was taken?
No, you know where. You know the coordinates and everything, but the image that you have, so these, most of the time, depends on how you collect the vector data. With tiger vector, I think they collected from satellite images. So they actually have, maybe they have a different resolution satellite image that they use that to extract these lines, and humans sit down and extract the lines, for example.
They actually drive. So
for Navteq, they drive. For Navteq, they do the driving, so they actually drive. For Navteq, I think they start with the freeways from Tiger,
right,
and then they drive the streets. So depend.
Well, So the question remains, right? Where do the errors come from? In the case of Navteq, it's like, is their GPS system faulty, or where
Well, it's not faulty, it just has inherent inaccuracies. So any measurement technique is going to have its own inaccuracies.
Well, I
and
understand
they're
that,
different.
but GPS is better than certainly that.
But this is not that bad, actually.
30 meters is.
This is not bad. This is 30 centimeter per pixel. So this is a pretty high resolution. So if you go, for example, to 1 meter resolution, you probably won't see much of a problem. So these problems show up when you actually go to detail. So Navteq is actually better. It's not that bad. But Tiger is that bad because, again, as I said, I mean, they collect this data from different. This is actually a very good question because originally when we were looking at this problem, we said, okay, we have the geo-coordinates of this thing, we have the geo-coordinates of that thing, we just put them on top of each other, they match. They don't.
A lot of it came from digitizing paper maps.
Right, so there are different techniques, digitization and then doing some raster to vector transformation and then filling up the rest. So there are all sorts of techniques people do, but that all of those results in, and then time is also another problem. You get some image at one time and extract the stuff and then you get the, this is interesting because we have a project from USGS, and USGS asked us to actually conflate their own vector data to their own satellite images. And we were confused. We said, how did you get these vectors? Didn't you get it from these images? Said, yes, but then now we have new images and they don't match anymore. So they actually pay outside vendors that they have this all these human resources that they actually go and fix things. For even USGS, where both sources actually come from the same place. So I agree, it shouldn't, but...
Well, no, I guess what I'm thinking about is the fact that your conflation, what you're doing here doesn't really make very many assumptions about the nature of the errors that are typical of these systems. Like if you were to say, for example, if you knew that it was just a matter of quantization error because the original satellite imagery was low resolution, that might actually inform sort of your noise model, and you might actually use that.
That's a good. I think there is another set of research that they are doing. They are trying to find the parameters that they parameters about how this image was captured, from what angle, and so on, and then the parameters for the other data set, and try to do that, basically, to use these parameters to fix it. But then they are limited to the sources where you have all sorts of information. If you just take it, I mean, our philosophy is that you get random stuff from the web, and you want to be able. So, in our case, we don't know anything about these things. We just got this image from this place and got this vector data from this other place. We want to be able to match it. But you're right. If you do have more information, you might be able to do a better job. Yes.
I don't see that what you just said there is entirely true. I mean, this rubber sheeting is basically assuming that there's some pretty simple parameterization of the error model between at least, in local areas. So, and that's a sort of, I mean, I think there's a model that sort of says that, okay, there was an issue in resolution with the two images, and there's maybe some angle problems that the photographs could have been taken at different angles. But within some reasonably large area, there's a systematic distortion. It's not like a random noise error on every intersection.
Right. So we do assume that
that's a kind of model of errors, right?
Right. So we do assume that within our local, like within the triangles, we assume that it's a single transformation. You're right. So the more control point pairs you have, the better the resolution of your triangulation, and hence the better the technique. However, working with these with real data, and as I said, we can look at the results we have. This is pretty okay. I mean, it's a reasonable assumption.
If you were to compare Tiger to the best sources you have or the best sources you construct, I would think you could build a sort of error model of Tiger that would give an answer to this question, which is that are the errors sort of randomly independent, or within some broad regions could they be explained by quantization error or a systematic shifts or angle kinds of
we didn't look at this as a kind of fundamentally, but I can tell you my intuition, but working with real data, that there is no global transformation. I mean, these things are, and that's not just us. This is like many years of GIS folks, that the whole reason for bringing up this the conflation technique is not ours, it's their technique. The whole reason for conflation and rubber sheeting is because of the fact that you do need these smaller local things. You cannot come up with something that say, okay, I just apply these errors.
I didn't mean globally over the whole thing. Within one of these map regions, I mean, it certainly looks like, and this is what I've seen elsewhere, that some simple shifts and
no, it's not simple shift. I promise you.
the fact that you're taking a median of those vectors is already a statement that there's something consistent across global areas.
There is a consistency locally, and I agree with that. But then it's not the fact that you, in a larger area, you can basically look at one area and say, okay, this is how things are shifted, and just apply it to everywhere else. And it's not usually the case. I mean, not usually, it's never the case. That would work. But again, I mean, we can look further and see, but the intuition is that. So this is now the Navteq data. So this is better accuracy, the red one. So you see it's not as off as the other one, but still it requires improvement, as I show you also with the other example with the Microsoft map point example. So I guess that's it for the first example. Let me go quickly through the second and third. These are actually quick, they're not as detailed. The second thing that we wanted to do was aligning raster maps with imagery. This is tougher because now we are talking about raster to raster conflation. So with the vector data, you did have the actual coordinates and lines and points and so on. With maps, you don't have that anymore. So one approach that we took, and this is based on the assumption that you have vector information about the area, is that we use the vector data of that area as a glue, if you may, so that you basically use the vector data to find the intersection points on the image, and then you also find the intersection point on map, and I tell you a little bit more about this. Now, here is an interesting problem. The problem with maps is that if you remember from vector to image, we said that we know the corner points coordinates. With maps, that's not even true anymore. I mean, for some maps you do, but for some maps you don't. So some maps that you get from the web, you don't even know the coordinates of the map. You know generally the area, but you don't know where exactly the map is. So even though you have the image which corresponds to this map, you still don't know the relationship between the map and image. And that's another problem that the approach we took was to say, okay, if I find all the intersection points on the map, think of this as some sort of a fingerprint of the map. It comes up with some unique set of pattern here that the pattern can be searched for in this other set of points. And then once you match that to this, then you can basically figure out where the image belongs in the map, or the other way around. Maybe it was the case that the map was a smaller area within the image. But either way, you do that with the point pattern matching. So what are the issues here? So this part I already talked about, to how to find the intersection points on the image. The part here is finding the intersection point on the map and then do the point pattern matching. Finding intersection on maps is also very difficult. It may look easy, but you have all sorts of things on maps. The major problem is all this text you have on the map that might get confused with roads. You have the background that you need to get rid of, and all sorts of things. So we look at a lot of techniques from the literature and put those together. Things like basically how to remove the background based on the, again, learning the colors and so on. Then decreasing the width of the line to get rid of text, so you stay with the rows, and then the reverse thingy, because now you need to thicken them again in order to be able to figure out the intersection points, and so on. So, and then having these different templates for intersections and search for those. So eventually, after all those, you can find the intersection on the map. And I'm not going to go through the details, but again, we have papers in this area if you're interested. And then once you find the patterns, then the problem is that you have a set of points here and a set of points here, and you want to find the matching between this to that. The exhaustive way of doing it is basically pick 2 points and find all the matchings, and then for each matching find the error of all the other points. and then pick the one with the smallest error. That is very complex, so we exploit a lot of information again from the maps. If you know the scale of the map, for example, you know the direction, you know distance, and so on. So using all these, we basically prune the search space, so you can do a reasonably good amount of time. You can find the pattern that matches. Again, if you're interested in details, I'm not going to the details, but we have papers on that. But here is the result, and I show you in the actual demo why this is useful. But just even here, you can see that if you do the matching between the two, certain areas, like for example, the fact that this is a park, you couldn't have that just by the image maybe, but once you have the satellite image, once you have the map, you figure out, okay, there's a park here. And then if you have only the map, you didn't know exactly about the structures inside the park, but now that you have the combination of two, you have both. So the idea is using the attributes of both. Another piece of work that we are now working on is to actually extract the text and then use the text to label the satellite imagery automatically. And these are for the places that you don't have any information. You have the actual vector data, but you don't know the labels of the streets and so on from the vector data. And this happens in foreign countries, basically. And then the last example is the some temporal data that we can use. And this is basically the three sources we use. One was a website that has all the train stations and their address on this is for Iran. And then you have vector data. This came from NGA of all the railroads. And then you have a third website that has the schedule of the trains. And this is what I showed you. And now the idea is that on each one of these sources, you cannot ask a question about, for example, when would be a train be in a specific area in a given time range. Okay, we cannot answer it here, you cannot answer it here, you cannot answer it here. However, if you integrate the three together, and that's what we did, then we can build a this is a GUI separate from GeoDec, so we haven't incorporated this into GeoDec yet. But basically, you can ask a query like this, a range query, and say, I want to see all the trains that would be in this area within this time interval. And it basically gives you the list of the trains and when the train enters the area and when the train exits the area. So that's another example of integrating sources from different places. You can now answer questions that you couldn't have answered before on any of these single sources. So this is pretty much, I guess, the three-piece examples. Let me quickly show you some of the screenshots of the current status, and then I show you the demo as my final. So as I told you, the first demo that we showed for GeoDec was June 2005. So the project actually started January 2005, so we are kind of like in 1 year. The first demo, we showed two separate pieces to NSF. We showed the integration of 3D model and the stat. This is the DC demo that I just showed you. I mean, this was a video clip, but the actual demo, you can navigate through it and so on. So we showed that one separately, and then we showed another demo that shows all the integration of different sources about that area, all the sources that I told you about. But then by October, for the USC's 125th anniversary, they asked us to do another demo, and this time the area was USC campus. So this time we actually not only integrated these two pieces together, so we do now have an integration of all these into the 3D models, but also we added some live video data. So when you come and see the demo, for example, at USC, you actually see, and Pushin was there, you actually see the live feed of videos all around the campus that you can, one of the demos actually is in my lab, and then the cameras are looking outside the lab. So you can go from the window and see what you see at the on the screen. And then one of them, actually, we had a couple of video cameras inside the building. So as you zoom into the building, you suddenly get into the inside the building and you see what's happening inside. So it was a cool demo. We did a little bit of temporal data here. So we got some live GPS data from USC trams that updated every 10 seconds. So we show those on the thing. We can't do query like the train query yet, but we just can visualize the location of the tram. And then we added a fancy gesture-based user interface. So you actually use gloves to navigate, like a Minority Report kind of interface to the system. So this is the 3D model of the USC campus and textures This is the first piece that I told, the first two pieces. Then we added vector data. We also added raster maps, and here the example we used was the tram road. And this is interesting because you cannot get the tram road in any other form except for map. So that gives a reason why you want to do maps. And it was a challenge basically to get this raster map and conflate it with the 3D model, but we did that. So it shows the tram road and all the stops and so on, as well as the vector data. Oh, another thing we did was we integrated some information from the web. It's not that big of a deal, but the idea was that as you move in close to the buildings, you get more information about the building, like the name of the building, the full name, and so on. And this was not hard-coded. This was not like that you already have the data in the system. It was as you get close, the system basically go to a web service that queries a website that has the information. So it was just an example of how you can integrate other web sources with the so this is an example, a very simple example of querying that you can do on the system right now. This is the trams, the blue lines, and their location. That was real time, and this is the user interface of the thing. So where we are going, this is my last slide. So I told you about RAISE, basically the challenges, and we are working on each piece, and then the blue ones are the ones that currently we are working on within the group that I told you, but the black ones are that we are going after other investigators at USC, Information Sciences Institute, and so on, to get their expertise and integrate that with GeoDec. And we already got some funding from Information Sciences Institute, ISI at USC, to support 4 more faculty to get their work integrated into GeoDec. So as as I told you, it's a very good framework for getting people integrate this stuff and show a nice kind of coherent story to outside for both marketing and getting fundraising. So let me just show you the video, and then we can. This is the USC campus demo, and as I told you, this is basically just a video. The actual demo, you can interact and you can zoom in and zoom out, but I couldn't show that part. So this is the 3D model of the campus. One of the commands you can do with the glove was to add different sources of data. So this I already told you, but this try to say how we do the conflation. So this is the vector data now mapped to the 3D model. You can change the texture. So here is the pre-conflation and post-conflation of the map, and then the result on the 3D model, so that you can actually see the. And this information didn't come. This is different from your from Google Hybrid, for example. This is not vector data. This is actually map on the image. As you zoom in now, this is the query part. You see that right now none of the buildings have any name associated with them, but as you zoom in, you start seeing names popping up.
where did you get multiple images?
This one actually we purchased. I don't remember what was the source, but this one we paid.
It was some set of aerial images taken in slightly.
There were two big aerial images of not just the campus, actually a large area around the campus.
Okay. But they were taken from sufficiently different enough viewpoints.
I think so. That's something that we asked Ram to order the images himself, so that we make sure that
No.
So I was not involved in the actual identification. For us, it doesn't matter. As long as we had a sound image, we could have done it. So we did all the fusion with those images as well. It's like, so usually like the image that but he did the one too, so I think it was even stereo. I mean, stereo works best for him. The system doesn't need stereo on its own to not from different angles and calculate the height and stuff.
That's pretty cool.
Other questions?
Okay.
Let's go ahead.
He's pretty close. Yeah, feelings.